We've all heard the saying, a watched pot never boils. But what if it actually boiled faster when you watched? Of course, in our macroscopic world, watching or not doesn't make a difference. But in the quantum world, where we consider the energy levels of an atom, active measurement can make a difference. Here we can consider the case where an electron jumps from a higher energy level to a lower energy level, emitting light in a process called spontaneous emission. We can ask, does the act of measurement change how the atom jumps? And it turns out it does. It's called the quantum Zeno Effect. This is when frequent measurements of the atom's state actually alters the atom's behavior, decreasing the probability that the atom might jump to the lower level, and on average, slowing the decay process of this transition. Each time we measure the atom to be in the excited state, we collapse the quantum wave function of the atom back to the excited state, thus resetting the clock of its decay process. And if measured often enough, the atom will never transition to the lower level. However, as predicted in 1997, there's also the possibility that frequent measurements can make the jump of the atom more likely, thus accelerating the decay process. This is known as the anti-Zeno effect. Now to talk about why the atom might decay slower or faster, we first have to examine why an atom transitions in the first place. We've talked about the atom already, but in order to understand why it decays, we have to consider the environment. The environment contains electromagnetic modes extending through all space that can contain any number of photons all at the same frequency. When an atom decays, the emitted photon escapes into the environment and will propagate in one of these electromagnetic modes. When there are fewer of these modes near the transition energy, the atom decays slower, but if there are more, the atom decays faster. To study the Zeno effects, we created an experiment with a cryogenic microscopic circuit, which has energy levels just like those in the atom we discussed. We probed the energy state of the circuit by shining microwave light at it and seeing how it reflects back. This process of measurement physically disturbs the energy levels of the circuit. To see how Zeno effects arise, we created a situation where the electromagnetic modes were not evenly spaced. In one case, where the measurement perturbation allows the photon to access on average fewer modes, we observed the Zeno effect, where the decay was slowed. Yet on the other hand, when the measurement allowed the photon to access more modes, we observed the anti-Zeno effect. Now to summarize, we can consider how this would affect Schrodinger's cat. Say we set up a box which contains a radioactive atom, a vial of poison, and a cat in such a way that if the atom decays, the cat will be killed. The Zeno effect says that if we check on the cat, then we reset the atom's decay clock, thereby preventing the vial from breaking and keeping the cat alive. Unfortunately for the cat, if we measure it quickly enough, then we might actually accelerate the atom's decay and bring about the cat's demise even faster. Because the Zeno effects have to do with the disturbance of the measurement and not the information, it turns out that it isn't even necessary to look inside the box, and the same effects will occur if you just shake the box.